Well, hi there. Today we're going to look at one of my favorite theorems in calculus, the intermediate value theorem. So let's begin by sharing this screen right here. And at this point, you see the intermediate value theorem. And let's read this together, okay? If f is continuous on the closed interval a through b, and k is any number between f of a and f of b, there is at least one number c in the interval a through b such that f of c is equal to k. Um, that may sound like a mouthful, but I think if we look at an intuitive understanding of the theorem, it will be rather straightforward, and I think you will enjoy working with it. So let's go ahead and scroll up a little bit, and here we are. Okay, draw 2 points that are not vertically or horizontally aligned. I'm going to scooch this up a little bit more. And you can do this on your paper. I will do it along with you. Since we're in this virtual setting, it's a little bit more interesting. So we have 2 points, and they are not vertically or horizontally aligned. Now, the part B, draw a horizontal line between the 2 points. Let's change the color on this. And so here's a horizontal line. It could be any horizontal line between these 2 points. And now that is completed. So let's take a look at part C. Connect the 2 points with a continuous curve without crossing the horizontal line if possible. So this, if possible, gets me to perk up, because if I'm attempting to connect these 2 points, let's call this point 1, point 2, I'm actually finding it impossible to connect the 2 points without crossing this line. And this can be, of course, done by just connecting with a straight line, or we can, of course, be a little bit more ingenious and then, of course, make that connection. But in any case, it doesn't matter how I do this. We end up with the connecting curve crossing the horizontal line that we drew. And that's really the gist of the intermediate value theorem. And here we have 2 different depictions. Let's take a look at this. On the left, this side right here, f is continuous on the interval a through b. There exists 3 c's such that f of c is equal to k. So just to help us out, make sure that we're looking at the same thing. We have y equals k right here. This horizontal line, y equals k. And then, of course, that quantity is actually reached at 3 different locations inside the interval a through b. And so this is an existence theorem. It tells us that if the necessary conditions are met, that there's at least one x equals c inside the interval a through b where f of c is going to equal k. And of course, the k value is a y quantity, and it would be somewhere between f of a and f of b. I don't know, depending on the function, whether f of a or f of b is bigger, but k would be certainly located inside. But the one condition that is absolutely necessary is that our function f be continuous on the interval a through b. So we have on the right another depiction. Here, the f of x is discontinuous inside the interval a through b, and as you can see, it is not guaranteed. There is a failure for this function to have a quantity, an x-coordinate of c, where the f of c would be equal to k. But the reason why that is so is because this function fails to be continuous inside well, this is actually y equals k, but the function certainly does not contain that value. In other words, there are no c's such that f of c is equal to k. So it's a very intuitive function. Unfortunately, when we get into the meat of the problem, sometimes students are a little bit confused. So what we'll do is we'll look at a very simple example that's more like a textbook example, and then we'll walk through a couple of actual AP calculus questions. So here's our first example, very textbook-like. Let's read the instructions. Verify that the intermediate value theorem applies to f on the indicated interval and find c guaranteed by the theorem. Okay. So we're presented with an algebraic expression of f, and f is equal to x squared plus x squared over x plus 1, and the interval in question is x equals 2 to 5 inclusive. These theorems always require a closed interval, and f of c is equal to 3. Well, first and foremost, we must establish that f of x is continuous on the interval 2 through 5. F of x does have a continuity issue, but that is at x equals -1, where the denominator would be 0. So I think we can establish that f of x is continuous on the interval, and let's get that spelling straight, sorry. And I will write this actually as such, so that way there's no misunderstanding that we are including the endpoints. And once, so f of x is continuous on the interval 2 through 5. This is a necessary condition for us to use the theorem. The other condition is we need to know what the y coordinates at the endpoints are. So let's go ahead and actually find out. F of 2 is equal to, I have a 4/3, and f of, let's see, the other endpoint is 5. So we end up with 25/6. Okay, so the other condition that we must absolutely have is that the desired quantity, in this case, the y coordinate of 3, has to be between the y coordinates of the two endpoints. Let's double check. So 4/3 is indeed smaller than 3, and then of course 3 is smaller than 25/6. 18/6 would be 3, so 25/6 is bigger. So consequently, the two necessary conditions to apply the intermediate value theorem exist. Consequently, we can go to the conclusion of the theorem, since the hypothesis exists, and then indicate that therefore by IVT there exists at least one C, and C, so there are a couple of critical things. We have to identify the two components of the hypothesis, that F is continuous on the interval, and we have to talk about the interval from 2 to 5. The, regurgitation of the theorem that F or even some other generically named function is continuous from A through B. You do not get credit for that. It's important that we students recognize that you need to pull the information from the problem to make sure that the person looking at your work understands that you are indeed in the problem being presented. And so we've established that f of x is continuous on the closed interval 2 through 5. We've established that basically f of c equals 3 is what we're trying to double check to make sure that this y value will actually be the value of our function f somewhere inside the interval 2 through 5. And we've certainly highlighted the fact that the y value of 3 is inside, f of 2, which is 4/3, and f of 5, which is 25/6. If you're absolutely wishing to record that this is f of 5, you certainly can, and that this is f of 2. by all means. You don't need to. And then we need to invoke the name of the intermediate value theorem. So by intermediate value theorem, there exists at least one C, but now we must identify on the interval where C has to be inside, okay, 2 to 5, such that f of C is equal to 3. Notice I never indicated whether it's 1, 2, or 3. We don't know. All the intermediate value theorem tells us is that there's going to be such a value. And looking back at the drawing that we see here, or the one that we made here with the 3 conditions that you have there, obviously this is something that must take place. We have a gut feeling, but your points on assessments and homework will be determined by you, not only using your gut feeling, but actually verifying that the necessary conditions are there, and then invoking the appropriate conclusion derived from the intermediate value theorem. Enough cheerleading. I think the way we get better at this is to actually look at problems and work problems. And here are a couple of actual former AP Calculus questions. And what I'd like to do is walk you through them. Some of them are very easy. You'll notice that we have, for example, tabular presentation, and you'll find that there's a lot of these on the AP test. Let's read this question. Let's do it together. And so the function f of x is continuous on the closed interval 0 to 2. This is wonderful. One of our necessary conditions, the continuity of on a closed interval, has been ascertained in the problem. Okay, continuing. And has values that are given in the table below. So we're not actually hunting for certain y values. Ordered pairs are given to us here. And let's see what the question is. The equation f of x equals 1/2 must have at least 2 solutions in the interval 0 to 2 if k is equal to what number? So we have to find the right value of k. I personally wouldn't spend a lot of time procrastinating. What I would do is actually graph the 2 points. And we can be very generic. What 2 points? The ordered pair of 0, 1 and 2, 2. I'm not going to graph the middle ordered pair because that's the ordered pair of 1 and k. We're actually looking for the y value, f of 1, which is equal to k. So if we want to write down f of 1 equals k, and we want to know what k is, that's grand. But at this point, 0, 1, so we have perhaps 0, 1, and then we have, I'm going to make this a little bit longer, the horizontal intervals, and then of course we have 2, 2. All right, and we have a line at y equals 1/2. That's right here. So now we're looking at, of course, proposed values of k, which are 0, 1/2, 2, and 1. And clearly, if there needs to be minimally 2 solutions, then the curve connecting the 2 points that I've drawn needs to actually cross this curve or this line y equals 1/2. And so consequently, to guarantee that that you are going to end up with 2 solutions, we need to have, let's see, 1/2 would not be enough. That would perhaps maybe make a tangent line there, and that would of course give you 1 solution. We could let's see, put 2, but if you put 2, that doesn't guarantee anything, not even 1 solution. And let's see, if we draw 1, well, again, that wouldn't really help us, because that would give you a point somewhere here. And again, all we're looking for is something that would guarantee that there will be 2 points of intersection. And you could perhaps have, 2 tangencies like this, but unless this value of f of 1 is smaller than 1/2, there is no guarantee of 2 points touching or crossing this horizontal line, y equals 1/2. So really the only answer that is suitable here for us is A, because if the y coordinate is 0 at 1, in that case, the curve has to cross, even if its most simplest form, at least in 2 places. And so f of x equals 1/2 must have at least 2 solutions. Those solutions, going back to Algebra 1, the solutions are represented by points of intersection between f of x equals, let me see, f of x being this curve that I've drawn, and of course the y equals 1/2, okay, the value of k. So I hope you're happy with that. I'm going to continue. We have a couple of extra questions here, and I'd like to eliminate a couple of responses. For example, the response here as part B is a wonderful response, but in the future. Right now, I thought this was a great question anyway for us to use in terms of the intermediate value theorem and learning more about it, but part B is not an option. We would not know how to respond to that at this point. We will shortly. But let's just go ahead and enjoy problem number 2 with options A, C, D, and E. And the problem reads as follows. Let f be a continuous function defined on the closed interval -3 to 6, where f of -3 is -1 and f of 6 is 3. So this is awesome. They've told us all the necessary conditions that f is continuous from -3 to 6. We've been given the y coordinates at each endpoint, and then the intermediate value theorem guarantees that. So what does the intermediate value theorem say in its conclusion? Okay, does it say that f of 0 is 0? I don't know about that. All I know is it tells us that there's at least one solution to any f or any y equaling a number between -1 and 3, because those are the y coordinates at the endpoints. Certainly 0 is one of those, but the issue that I'm worried about here is that they've connected the y coordinate of 0 with the x coordinate of 0, and the intermediate value theorem never guaranteed that we would know what x coordinate is paired with this y coordinate. So I'm going to put a question mark here. I'm very nervous about choosing that one. Then moving on to C, that between x equals -1 and 3, okay, no, no, it's not X. This part C right here, I'm seeing that, let's see, the Y coordinate is between -1 and 3 for all X between -3 and 6. Again, I find that these problems are so challenging for me. I'm ready to embrace all of them and say yes, but if I carefully draw this, okay, remember what is suggested here, okay, that this is going to be the highest value or the value of the endpoint here. And so that's y equals 3. This is the lower value, y equals -1. And so answer C is indicating that between this vertical line is x equals -3. This one is x equals 6. So this statement C is guaranteeing that the function f is going to have y values that are between -1 and 3 on the entire interval between x equals -3 and x equals 6. I don't think that that's one of the stipulations of the theorem. I believe you can have functions that actually go outside of that interval. In fact, we don't even know how many times they could go outside. Many times. Okay, the only thing the theorem tells us is that basically if f is continuous on the interval from -3 to 6, and we're proposing a y value that is between -1 and 3, that in that case, there's guaranteed to be an x value between -3 and 6 that will be associated with that particular value of the function. And here we see that there are 3 c's, so maybe c sub 3, c sub 2, and c sub 1. I don't think that I can go with c as an answer. I'm going to eliminate that. Now we're going to analyze f of c equals 1 for at least one c between -3 and 6. Okay, so we've established the continuity. F is continuous on the closed interval. And indeed, if we're looking at part D, you've got -1 is between the endpoints. Let me see, not -1, it's a +1 here. And so +1 is indeed between the 2 endpoints, the y coordinates of the endpoints, which is -1 and 3. So this is a true statement as well. That means that the intermediate value theorem applies. So this is my choice. But out of curiosity, I'm actually going to go to part E as well. And we have f of c equals 0 for at least one c between, let's see, -1 and 3. And so let's see what we have. F of c equals 1 for at least one c between -3 and 6. Okay, that's good. And for at least one c between -1 and 3 here, I think they're trying to trap us. How are they trying to trap us in part E? They're highlighting here the values of y. These are values of y, and c is an x coordinate, x equals c, and these are y coordinates. We need to make sure that here the numbers should be not -1 and 3, but -3 and 6 would have been the way to go, okay? And so that was a mistake there in the answer, but we as learners needed to identify that. So we really need to understand the theorem not only intuitively, but then of course go and look at the problems in great detail. Moving forward, okay, Steve runs back and forth on a straight track. His velocity measured in meters per minute is given by the continuous function v of t, where t is measured in minutes. Select values of v of t are given in the table above. Do the data in the table support the conclusion that Steve's velocity is -10 meters per minute at some time t, with t being between 4 and 5. So let's take a look at it. 4 and 5. So we're looking at these two columns and give a reason for your answer. So I believe that the answer is yes. Okay. And the reason is as follows. Okay. We are told that, let's see, v of t is a continuous function, okay? So I would state in my justification, yes, because v of t is continuous on, and the interval needs to be 4 to 5, and we need to include the boundaries, so equal to must be part of that symbol. Spelling must be correct. We must be using t, not some other variable. So yes, because v of t is continuous on the interval 4 to 5, and we have, let me see, v of 4 equals 30, which is greater than, let's see, I think we're looking for -10. And -10 is greater than -15, which we are pulling from v of 5, okay, from the table. So these are the necessary conditions for the intermediate value theorem, the continuity on the closed interval, and of course the y coordinates of the endpoints, one being greater, one being smaller than the value that we're seeking here, which happens to be v of t equals -10. So therefore, you must invoke the name of the intermediate value theorem. Therefore, by IVT, there exists at least one t where, and I think I need to be more careful, at least one t on interval, and let's put the t inside the interval 4 to 5, such that v of t, or did they use a different letter? We can certainly do v of t, such that v of t is equal to -10. Okay, but all of these things are necessary. I think we've discussed the necessity of stating the hypothesis that v of t is continuous 4 to 5 inclusive, that basically v of 4 is greater than -10, which is greater than v of 5. But the other component has, okay, the following. We need to use the name IVT, okay, and we need to identify the fact that t is located, okay, that there exists at least one t, okay, but that this t is inside the interval right here, and that, of course, v of t will be -10. So if you've done all of those, that's 4 different components. If you've done all of those, then you have nailed it, okay? It gets easier the more you do, but as you can see, there's a little twist to each problem, and that's why we do problems, so that we can become strong, okay? So number 4, and if you say, no, I want to do number 4 first, this may be a great time to pause your video, and then of course after you're done, then you double check to say, did I nail this? Okay, so if you're a pauser, this is where you pause, and if you're not, or even if you are, welcome back. Let us continue. So number 4, water is leaking out of the broken pipe. The rate that the water is leaking out is given by the continuous function L of t, where L is measured in cubic feet per minute and t is measured in minutes. Select the values of L of t. Select values of L of t are given in the table above, and so the question is there a time t on the closed interval 3 to 6 at which L of t is 15? Justify your answer. So guys, I am actually zeroing in on the interval between 4 and 6 because here the values of L of t sort of straddle 15. And so what do we need? Remember, the necessary conditions. Okay, number 1. Oops, I don't want to use that, sorry. Number 1. You don't have to number these. I'm just trying to make sure that communication is a little bit easier between you and I, but L of t is continuous, and you can make a greater interval that than 4 to 6 and assert that the L of t is continuous, but you have to be careful not to include intervals where potentially L of t would be discontinuous. All I need to do on the narrow sense, since we're looking at the t equals 4 and 6, is to indicate that L of t is continuous on interval. Let's see, t is between 4 and 6. Again, I could have expanded that to 0 and 6, but boom, there we are. And later on, we'll need to, of course, focus in on the more narrow interval in any case to get the correct answer, so might as well do it from the beginning. So L of t is continuous on the closed interval 4 to 6, and let's see, I think we'll come down here. So part 2, L of 4, which is equal to 14.1, is less than the fabled 15. We're looking for L of 15. And then, of course, that is greater than, no, less than, sorry, less than 15.8, which is, of course, pulled from L of 6. Okay, so we've established the two necessary conditions. Once we have that, then therefore by IVT, you have to use the names of our theorems always. So therefore by IVT, there exists at least one, and then we can of course use at least one C or at least one T, where T is between, and this is the important part. A lot of people indicate where T is, at least one T that is, but they forget to fix T inside a certain interval. Here it has to be between 4 and 6, and that can only be 4 and 6 because it needs to be the narrowest interval. So you can't be using anywhere between 0 and 6. That would be wrong. You only get credit for using 4 and 6. Okay, so there exists at least one T where T is between 4 and 6, and you don't have equal to here, such that L of T is equal to 15. Where did the 15 come from? From here, okay? All right, and so at this point in time, we're done with another problem. And if you tried this on your own by pausing the video and now you came back and you got it perfect, well, you celebrate. But even if you didn't get everything right, you celebrate because you're getting feedback and we're learning and getting better, okay? So continuing, this looks like it's a little bit harder, but just look at this as the table organized vertically, and we have F and G. So again, that's why spelling needs to be very, very important. Also, we have a function called H here. So we need to be careful with what we name things. But let's take a look at this. The function f and g are continuous for all real numbers. The table above gives values of the functions at select values of x. The function h is given by h of x equals f of g of x plus 5. Explain why there must be a value s for the interval 1 through 7 such that h of s equals 1. Well, first and foremost, we're talking about h, okay? And this is the interval. So consequently, okay, we must establish the fact that since f and g are continuous, their compositions, and of course the addition of 5, will result in a continuous function h. So the first statement that I'll make, again, you don't need to number these, but h of x, or we could indicate since f of x and g of x are continuous, therefore h of x is continuous. And I didn't mention the interval earlier. That's okay. I need to mention it either earlier or now. So I will now indicate h of x is continuous on interval. And the continuity will be inclusive. And let's see, it will be from 1 to 7, okay? And so once we've established that, then let's continue. The other component needs to be that we need to identify h of 1 and h of 7. So let's go ahead and work on that. I've got h of 1, and I need to find, let's see, g of 1. And so g of 1, let's take a look at it, is right here, okay? That's g of 1. And so we are able to go ahead and identify that as f of 10 and plus 5. And f of 10 is given to us right here as 2. So once we have established that, then we have 2 plus 5, which is 7. Okay, well, 7 ends up being bigger than 1. And remember, we are seeking this quantity here. okay? And so continuing that quest, let's see what we have. I will now need to do a little bit of work to actually identify what is h of 7. So h of 7 is going to equal to, let's see, f of g of 7 plus 5. And I think we're getting a little better at this. So we're looking for g of 7, and g of 7 happens to be 3. And so let's see, that gives me f of 3 plus 5. And I'm afraid I'm running out of room here. So we'll go a little bit lower. And f of 3 happens to be what? It looks like f of 3 is negative 10. So negative 10 plus 5, I'm getting a negative 5. Okay. So this is cool. Then intermediate value theorem applies because h is continuous on the interval negative 1 to 7, inclusive. And let's see, I also have the h of s equals 1, so 1 is between the y coordinates of the endpoints, so between 7 and negative 5. So therefore, by IVT, there exists at least one, and I think they're using S here, so we'll go at least one S, and then we need to, of course, indicate that S is between the 1 and 7, such that h of s is equal to 1. And so you're done. That was awesome. That was a lot of work. I think most of the work, however, was simply dealing with the composition of functions and pulling values from the tables, and we did a good job. Now, we're getting to the end of our journey. As you can see, this is it. This is simply the essential knowledge. So let's go ahead. And again, if you say, look, I love these multiple choice questions. They really test my understanding deeply about the intermediate value theorem, then you'll just want to pause this video and actually get into the problem and see the results. And then, of course, I'll pick up immediately. So those of you that do not want to do that, you just don't have that confidence yet, will be able to go ahead and continue. So number 6, here we are. Okay, let f be a function that is continuous on the closed interval 2 to 4 with f of 2 equals 10 and f of 4 equals 20. But by the way, this is not unusual for them to give you all the necessary conditions that you have to have with minus 1 or 2 little tidbits, okay? So which of the following is guaranteed by the intermediate value theorem? So it might actually be beneficial to understand that, okay, so the continuity on the interval 2 to 4 is there, that because of the given endpoints, okay, so the y values are from 10 to 20, so therefore this f of c, magical f of c, is going to have to be in between 10 and 20. That's the only thing that the intermediate value theorem talks about. So maybe this will help us narrow down the correct answer. And I think I actually have to eliminate 2 answers here, but that's okay. This is still a phenomenal problem. That's why I included it here. And why am I eliminating these problems or answers? Well, because they have these little notations that we don't know what the notations mean or what the concepts mean. We will shortly, but right now we have choices A, B, and C, and this is still a wonderful problem to test our knowledge and understanding of IVT. So let's see. Again, which of the following is guaranteed by the intermediate value theorem? Please keep in mind when guaranteed must happen, that means if there's one exception, then this is not true. So guaranteed must mean absolutely. So A, f of x equals 13 has at least one solution on the open interval 2 to 4. Okay, so 2 to 4 is indeed the interval, okay? And f of 13, well, that's between 10 and 20. Guys, I'm getting all excited. I think A is our answer. But you know, we're not gonna drop it that fast. We're gonna continue looking at the other answer choices and learn from why we would eliminate them. Okay, and this was key to my decision making here. The fact that we were looking for an FFC that was between 10 and 20, and clearly 13 is it. And also, we really want to be careful and highlight the fact that this said f of x, which is important in the sense that it didn't say f of 3 for perhaps, because that means you're only focusing on a certain coordinate, and IVT doesn't tell you where this magical x coordinate is. It just says it's somewhere between x equals 2 and 4. So continuing, let's take a look at part B. F of 3 is 15. Again, that's a problem. Yes, 15 is between 10 and 20, but they're nailing it to a particular x coordinate, and no, that's not guaranteed, okay? The intermediate value theorem doesn't tell you where to find that particular value of c. In fact, we'll go back to our first example and take a look at how one would solve it. That is a typical textbook problem, but it is never a problem that will be asked on the AP test. At least it hasn't been in the recent years. By that I mean 20 years or so. So let's see. Part C, f attains maximum on the open interval 2 through 4. Again, this is not an extreme value theorem or anything like that. This is simply the intermediate value theorem. So this is a pretty bad distractor, and we're going to rule that one out, although that one was pretty phenomenal. So this really brings us to the end of our intermediate value theorem journey, except that we're going to go back to the first problem that we looked at, and there we actually have the incentive here. I think they tell us that find the C guaranteed by the theorem. Okay, so how would you actually find that C now that we've established that the intermediate value theorem can be applied down the interval? The answer is very simple. It's basic rudimentary algebra. That's why I omitted that the first time, but nonetheless, I need to make sure we get this. So we take the x squared over x plus 1, and we set this equal to 3, y3, because that's what they had here for y. And then we start solving our basic algebra skills. X squared is equal to, let's see, 3x plus 3. This is a quadratic. We want to get 0 on one side. And I'll tell you what, I did not use the quadratic formula. Instead, I simply graphed this with my graphing calculator, and this needs to be done correctly. Graphed this with my graphing calculator. I put the x squared minus 3x minus 3 into the equation editor. And then, because unfortunately, we make mistakes. For example, with the quadratic formula, you would end up getting 2 answers. And if you submit an answer as a potential value of C, but it does not reside inside the interval that you are looking at, and in this case, you're looking at the interval 2 to 5, in that case, you're going to lose points. So I set my window in the graphing calculator to go from 2 to 5, and I ended up with the following answer. There was only one, well, because I was looking at that right window. With the quadratic formula, we would be able to come up with 2 answers, but we would have to kick to the curb any value that would not be inside the interval 2 to 5, okay? So the answer that I obtained was 3.791. And one of the things that we probably should alert you to right now, anytime you're doing a calculator problem, we're expecting a presentation that has 3 decimal digits unless the problem actually tells you to round off to the nearest whole number, okay? All right. So this brings us to the end of our journey. It has been a true pleasure working with you, and looking forward to seeing you again soon. Thank you very much.